Welcome to Understand the Math. If you're gearing up for an exam and need a quick review of linear transformations, you're in the right place. In this video, I'll break down the key concepts and highlight what you should know before your test. And if you're looking for more detailed explanations or additional practice problems, check out my full linear algebra series that covers these topics thoroughly. Let's get started. The first topic that I'm going to review is an introduction to linear transformations. If a transformation is linear, it can be written as a matrix transformation. Matrix transformations map vectors from one vector space to another, or possibly the same vector space, using matrix multiplication. The formula that you need to remember for this is T of x is equal to matrix A times vector x. Let's now talk about some terminology that goes along with this. A linear transformation will map a vector x to a vector t of x, which is equal to ax, and we also call that vector b. X is an n by 1 vector, A is an m by n matrix, and that way the two can be multiplied together, and then our t of x, or our b, is an m by 1 vector. So we say that b is an element of Rm, and then x is an element of Rn. Those are going to be important in the definitions that we're going to go over right now. The domain of a linear transformation is the set of all possible input vectors, and those are Rn. Our codomain is the set of all possible output vectors, or the vector space that the transformation maps to, and this is going to be Rm. In practice, if you need to find the domain or codomain of a transformation, you need to look at the size of matrix A, because that's going to give you Rn and Rm, because remember that A is m by n. The image or range of a transformation is the set of all actual output vectors, and this is a subset of the codomain, and this is just vector b. So in practice, to find the range or the image, all you need to do is you're going to take your matrix A and multiply it by your vector x. Lastly, we have the preimage. The preimage is the set of all actual vectors in the domain of a transformation that map to a specific vector in the codomain, such as our vector b. This seems a lot more complicated than it is. The preimage is just vector x. So if you're having to find the preimage, in practice, what you're going to do is you're going to take A, augment it with matrix B, put it in reduced echelon form to find your vector x. Let's now talk briefly about how a transformation is a linear transformation. A transformation T is a linear transformation if it preserves the operations of vector addition and scalar multiplication. These properties are written algebraically like this. I want to point out something about the second property. Notice that if C is 0, then T of 0 is going to be equal to 0. This means that the origin is going to remain fixed. To see if a transformation is a linear transformation, all you need to do is let U be equal to U1, U2 if you're in R2, and then let V be V1 and V2, and then substitute these back into properties 1 and 2, and then see if the left-hand side is equal to the right-hand side. I want to point out that if a transformation cannot be written as a matrix transformation, then it is not a linear transformation. All linear transformations can be written as T of x is equal to A times x. Linear transformations modify vectors in a way that preserves the underlying structure of the vector space, such as straight lines, the origin, and linearity. This is the same as saying that all grid lines remain parallel and the origin remains fixed. Let's now review the concepts associated with the matrix of a linear transformation. We're going to begin by reviewing standard basis vectors. The standard matrix of a linear transformation contains transformations of vectors that are called standard basis vectors. They're just unit vectors, which means they have a magnitude of 1, and they point along one of the coordinate axes. For example, in R2, we have two standard basis vectors, and they are E1 and E2. You might know these as I hat and J hat if you studied physics. I've plotted these vectors down here. I hat or E1 goes in the X direction, and then J hat or E2 goes in the Y direction. And those are our standard basis vectors. Any vector in R2 can be written in terms of these standard basis vectors. So we can write a vector xy as x times E1 plus y times E2. This happens for all the other dimensions as well. So any vector in Rn can be written like this. There's our x vector. It has components x1 to xn, and we can write it in terms of n standard basis vectors, E1 all the way up to En. This next part is super important. When we're working with linear transformations, if we know how the standard basis vectors transform, then we'll be able to determine how any vector transforms. And that's what we're going to look at next. We're going to use standard basis vectors to find the standard matrix for a linear transformation. This is a really important concept to remember. If we have a transformation T that maps vectors in Rn to vectors in Rm, we can write T of x as equal to A times x, where our matrix A is an M by N matrix. This matrix A is called the standard matrix for a linear transformation. I've written this down here in red, and this is a formula that you definitely want to remember. Our matrix A is just the transformation of E1, E2, all the way up through En. And one thing I always tell students is remember that this is in your first column, second column, all the way over to your nth column. Once we know matrix A, all we have to do is multiply this matrix A times our vector x, and we're going to get vector T of x. What we're going to do now is go over some common geometric transformations. The first one that we usually go over is called reflection transformations. These are just geometric transformations that flip vectors over a specified axis, line, or point, producing a mirror image of the original vector. Let me show you what this looks like when we do reflection about the x-axis. We have a vector x, we're reflecting it about the x-axis, and we get vector T of x. Now what we need to do is try to figure out what is the matrix A that enables us to multiply A times vector x to get this vector T of x. And that's our standard matrix that I've listed right down here. Now we're going to figure out what it is. So the idea is we're going to take E1 and E2, and we're going to see how they transform. So notice E1 lies along the x-axis. So if we flip it about the x-axis, it's going to stay the same. So its components are 1, 0, and that goes right up here. Now, something's different is going to happen to E2. E2 is going to flip down here because it's going to flip around the x-axis, and it's going to have components 0, minus 1, and then we put that in the second column of A because that's T of E2. So now we found our A. You can do the same thing to reflect about the y-axis. We can reflect about the line y is equal to x, and you can find what matrix A is equal to by looking at how E1 and E2 transform. The next transformation that we're going to look at is projection transformations. These are geometric transformations that just project vectors onto is the key word, to a specified axis or line. Let's look at projection onto the x-axis. So what's going to happen is we're going to have our vector x and we're going to project it down here onto the x-axis, and we're going to get t of x. To find the matrix A, we have to think about E1 and E2. E1 lies along the x-axis, so it's going to stay the same. And then E2 is going to have to go down to the origin, and so the second column of A becomes 0, 0. We do the same thing when we project onto the y-axis. When we do that, E1 goes to the origin, so that vector becomes 0, 0, and then E2 stays the same, so that's just 0, 1. Now let's review rotation transformations. A rotation transformation is just a geometric transformation that rotates vectors in a circular motion around the origin without changing their distance from the origin. And I have this plotted here. We're first going to look at counterclockwise rotation. So what's going to happen is we're going to see how E1 and E2 transform. E1 is right here. It's going to transform to t of E1. And using trigonometry, we can see that that point is going to be cosine theta sine theta. So that goes down into our first column. Then we're going to look at E2. This one's harder. It's going to rotate counterclockwise, and it's going to become this point, which then goes into our second column because it's t of E2. We can also do the same thing and rotate points clockwise. And when that happens, t of E1 is going to be in our fourth quadrant. So we're going to have cosine theta minus sine theta. And then t of E2 is going to be in our first quadrant. And we pick up a sine theta, cosine theta. The last geometric transformation that we're going to look at is contraction and expansion transformations. A contraction transformation scales vectors. That's key, so let's highlight that. It scales vectors by a factor less than 1 because it's contracting. And then an expansion transformation scales vectors by a factor greater than 1 because it's expanding and it's going to grow or stretch. Let's first look at a horizontal contraction and expansion. For this transformation, t of E1 is the one that's changing because we're contracting or expanding horizontally. If E1 contracts, then our k is going to be between 0 and 1. And if our E1 expands, then our k is going to be greater than 1. Our t of E2 is going to remain the same because nothing is happening vertically. When we contract and expand vertically, just the opposite happens. Our t of E1 doesn't change because nothing's changing horizontally, and then our t of E2 changes in the exact same way it does when we did a horizontal contraction or expansion. The topic that we're now going to review is one-to-one and onto transformations. I always tell students when you study one-to-one and onto transformations, you need to know theoretically what is happening with these two different types of transformations. And then you also need to know practically how you can determine from a matrix if a transformation is one-to-one or onto. One-to-one and onto transformations tell us how linear transformations map vectors from one space to another. And they provide critical insight into how systems behave and whether solutions to problems exist. When we think about one-to-one and onto transformations, we're looking at a of x is equal to t of x, and we call t of x b. Remember that a is m by n, our x is n by 1, and our m is m by 1. So we say that x is an element of our n, and then t of x and b are elements of our m. So what we're doing with our transformation is we're mapping vectors in Rn to vectors in Rm. Let's first look at one-to-one transformations. I have this pictured here. When a transformation is one-to-one, each b is the image of one x. Let me see if I can highlight that. So here's a B, and it is the image of 1x. Likewise, AX is equal to B has a unique solution X. And practically, we can tell that this is going to happen because for a one-to-one transformation, every column of A has a pivot, and that's because we have a unique solution X. Let's now look at transformations that are not one-to-one. For a transformation that is not one-to-one, each B is the image of more than one X. So let's go up here to our graph. There's our B, and can you see that we have two X's that are mapping to that B? That also tells us that AX is equal to B has infinitely many solutions X. I just couldn't write an infinite number of dots. Practically, we can tell if a matrix is not one-to-one when we look at the columns. At least one column of A is going to have to be missing a pivot. Let's now look at onto transformations. A transformation is onto when each B is the image of some X. So basically what's happening is all of our B's are the image of an X. And that means that AX is equal to B is going to have a solution for all B. And that's going to happen when every row of A has a pivot. Now let's look at what happens when we have a transformation that is not onto. Not every B is the image of some X. So sitting up here hiding is this dot right there. That is our B that does not have an X mapping to it. And because of that, AX is equal to B does not have a solution X for all B. And this is going to happen when at least one row of A does not have a pivot. To determine if a matrix is one-to-one or onto, in practice, here's what you're going to do. You're going to take your matrix A, you're going to put it in echelon form, because echelon form tells us what type of solution we have, and we're going to check the pivots. If every column has a pivot, our transformation is one-to-one, and if every row has a pivot, our transformation is onto. The last concept that I want to review for you is called difference equations. Difference equations describe the difference between successive terms in a sequence. They are a discrete counterpart to differential equations where changes occur continuously, and they're used to model situations where changes occur in steps or what we call discrete time intervals, as opposed to continuous time intervals. These could be daily, monthly, yearly, or any other unit of time. We typically write a difference equation as vector x sub k plus 1 is equal to a matrix A times vector x sub k. Matrix A is called a transition matrix, and vector x sub k contains the information about the state of the dynamic system at time step k. With difference equations, you're typically given an initial state, which we're going to call x0. You may then be asked to determine what your state is going to look like 1 month or 1 day or 1 year in the future. In that situation, you're going to calculate x sub 1, and you're going to calculate that by multiplying matrix A times your initial state x0. Maybe then you want to go find out what happens 2 days in the future or 2 months in the future. In that case, you're going to calculate x2. And if we use the same formula, you're going to take matrix A and you're multiplying it by x1. But notice, we can substitute in this expression for x1 and get this formula, a squared times x0. The nice thing about this formula is we don't have to calculate the first step to find the second step. Where this really comes into practice is when we find a step in the future, say x sub k plus 1, it's going to then equal a to the k plus 1 times x0. Let's go over an example real quick so you can see what we have to do in practice to solve one of these types of problems. I've written down an example where we're given percentages for how fitness levels change for individuals each month. We're going to have unfit individuals fit individuals, and then what we call superfit individuals. The first thing that you're going to want to do when you solve one of these problems is you're going to create a vector. We're going to call it x sub k, and you're going to put what we call our state variables into that vector. The second step is you're going to create your transition matrix. I would suggest when you create your transition matrix, you take your states and you put them on top of each column of your matrix and then beside each row of your matrix. You then need to go ahead and enter the data. Let me show you what happens right here with this one. We were told in this problem that 70% of individuals that are unfit remain unfit. So we put a 0.7 there. We were then told that 30% of unfit individuals become fit, so we put a 0.3 there. And then we were also told that you can't go from unfit all the way to superfit, so that's going to be a 0. The same thing happens when you fill up the other two columns. I want to point out that each of the columns are going to add up to 1. Now, this is when your population does not change. If you're dealing with difference equations and biology type problems where you have species that are maybe dying off, your population is going to change, so your columns are not going to necessarily add up to be equal to 1. The third and final step then is to calculate your next state. So for instance, we can find our state 1 is equal to our matrix A times x0, and x0 is usually what we're given. This is our initial state. And then same formula that I showed you up above. If you want to calculate state k sub 1, that's going to be a to the k plus 1 times your initial state. I hope this video has clarified all of these concepts for you. If you're studying for your exam, be sure to check out my exam practice problems video. It's packed with example problems and could be a great next step in your preparation. Good luck with your studies.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.